Hello everyone, welcome back to lesson number 24 for Calc BC. In this lesson, we're going to do everything else just as a mixture of things, taking derivatives of crazy functions, how to take a derivative and integrate a function that it's a constant raised to an exponent, not e. And that's what we're going to do in these videos. So for example, number 9 and number 10, you do it the exact same way. I mean, yeah, you could absolutely use the chain rule here, 4 raised to this to the third power, and then use the quotient rule, and that's crazy. You can do that. That's absolutely work, but you have to do it again down here. It's just a lot of craziness that I'm going to show you guys a somewhat easier way of doing the problem, but I'll show you a different way of attacking this question instead of the traditional derivatives of chain rules and the quotient rule. But before I get to question number 9, let's look at this problem right here. So I'm going to take a derivative of a constant raised to a function. Now there is a equation, or actually a formula, that I'm going to show you in a second that's going to show you or shortcut you into doing these problems. But let's do one the long way so you guys can see what the actual derivative is, and then I'll show you guys at the very top here what you can immediately jump to. So just like before, we want to get the 3x down, so we're going to add the natural log to both sides, and we can absolutely do that. So we're going to go ahead and add the natural log to both sides. So natural log of y equals natural log of 5 to the 3x. I can go ahead and move the 3x down. And so now I'm left with natural log of y equals 3x natural log of 5. Now that we know how to take the derivatives of the natural log, we can do this, but we have to use implicit differentiation. So I'm going to go ahead and take the derivative of the natural log of y, which is going to be 1 over y dy dx, is equal to, now remember, 3 natural log of 5. That is a number. That is a number. So this right here is 3 natural log of 5 times x, right? It's times x. So the derivative of some constant times x is just going to be that constant. So this derivative, you don't have to use the product rule here at all, because this is a number times another number x. So it's 3x, 3 natural log of 5. And now if I want dy dx by itself, I'm going to multiply both sides by y. And so I'm going to get this times y, and then I already know what y is. So my answer is going to be 3 natural log of 5 times 5e, 5 raised to the 3x power. Okay? And this is the answer to your problem. So let me really quickly show you guys now the shortcut to this. And the shortcut is the following. So if you're taking a function and it's some a, and the a is a number, to some function f of x, so a is a number, so a is a constant, and our function's this, then our derivative is going to be literally what you see there. It's going to be a to the f of x, so you're going to plot that down. So there it is right here. You're going to multiply by the natural log of whatever a is. It's always going to work, the natural log of a. And then you're going to multiply by the derivative of your function. So your derivative of 3x is simply going to be equal to 3. And so this is your shortcut that you can do now, so you don't have to do this craziness again. Now, with that being said, let's look at this and approach it the same way we did here. Let's add the natural log to both sides. Now again, you can use your straightforward chain rule, quotient rule, fun thing for this problem, but if I do that, then I can go ahead and do the natural log of y equals 4 natural log of 10x cubed all over the square root of x plus 1. So I'm just moving the 4 down. And then the other thing I can do here, guys, is I can write out the natural log of 10x cubed minus the natural log of x plus 1 squared, or to the 1/2 power. And then I can find these derivatives independently of each other, right? I can find these derivatives independently of each other. So the derivative of, I'm going to move this down here, so the work for this is here. So the derivative of 1 natural log of y is 1 over y dy dx is equal to 4. The derivative of the natural log of 10x third, or x cubed, is just 1 over 10x cubed times the derivative of 10x cubed, so 30x squared. So that's our first little piece. Minus, well, I can move the 1/2 down, right? I can move the 1/2 down, so this is 1/2. So now I have to just multiply by the derivative of the natural log of 1 of x over 1, which is going to be 1 over x plus 1 times 1. And then I would multiply both sides by y, and y is this crazy function right here. So if I want to multiply both sides by y, then I would have a times y right here, but I know what y is. Y is this crazy function. So I'm showing you guys this way, this method, as another way of doing this without the craziness that was, what is. And this is actually somewhat simple to simplify here. We have, minus 1 over 2x plus 1. This ends up being 3 over x right here. So again, it still looks nasty. It's still a nasty derivative, but at least you guys can see the pieces a little bit better. So this is just another strategy, if you will, to solve this problem. Okay? So that's the idea for that problem. The question here says we could also find the derivative of x raised to the x power. Well, it could be any function with this. So we would do the natural log problem again with that. So let me actually write this as a new problem. So what is y equals x to the x power? Well, we can add the natural log to both sides. We can move the x down. So this is just telling you there's always, if you have some crazy function raised to another function, you can always implement the natural log of x. And now take the derivative of this. So again, 1 over y dy dx. You will have to use the product rule here. It's going to be the first times the derivative of the second plus the second times the derivative of the first. So I'm left with the right side as 1 plus the natural log of x. And I've got dy dx. I can multiply both sides by y. So, and we already know what y is. We know what y is. So it's going to be x to the x, 1 plus the natural log of x. So you can always do these crazy functions. When you have some function raised to another function, you guys can always do that by implementing the natural log. And that's the easiest way to do that. And notice that for every one of these questions, this left-hand side is always going to take the derivative. It's going to be 1 over y dy dx. So you're going to always multiply whatever your derivative is of this with your y. So you'll always have this back. So you'll always have the function back. So that's an easy way to spot whether the derivative is correct or not, is that do you see this in your solution? Because you always will. All right, so the last thing we're going to do, guys, is to integrate with a constant. And so I'll do that one next. So I did this example in video number 4 where I changed this to an e. Now I'm going to leave it as a 3. So your goal for exponential functions is to get it as e to the u du or e to the x dx. Well, your goal for these is also going to be your number to the u du or your number to the x dx. So we want to do that. So you're going to start this problem out just like you would if this had been e or any other function, as you still have your u is x squared. Your du is going to be equal to 2x dx, and you're going to have a 1/2 du equals x dx. So we're going to rewrite this as 1/2 the integration of 3 to the u du, and that's exactly what we want to see. We want to see that. Now, I'm just going to tell you guys that the derivative of e to the u is e to the u times the natural log of 3. The natural log of 3, right? Because that's what the pattern is I showed you guys on the first page. So when you're integrating this, you're going to still do e to the u. You're still going to have e to the u, but you're going to divide. You're going to divide by the natural log of 3. You're going to divide by that value. Because if you take the derivative, again, so just really fast, we just said on the first page that the derivative of 5 to the 3x, actually let's make it easier. Let's just make it 5 to the x, because this is what this is always going to be. So 5 to the x. Your derivative is going to be 5 to the x times the natural log of 5 times the derivative of x, which is going to be 1, which is why you need this as a u, as 1u, because then you don't have to worry about that part right here. So if I want to get rid of this, I have to divide by the natural log of 5 to get it back. And so that's why we have the natural log of 3 here. So this answer is going to be in the bottom 2 natural log of 3, and then e3 to the x squared power plus c. And you guys may see this, and I rarely doubt that you will, but you could see this as natural log of 3 squared, which would be the natural log of 9. Sometimes they do that. They simplify the pattern that you can move the 2 up and then simplify that way, but this is also equal to the natural log of 9. All right, so one more question for you. Example number 9, it says, if f is the antiderivative of x squared over 1 plus x to the 5th, such that f of 1 equals 0, then f of 4 is equal to what? This is a classic example where you have to use a calculator. And so if I'm integrating from 1 to 4, I'm going to integrate from 1 to 4 of the function. because this is the antiderivative. And remember, if this is the antiderivative of, if f is the antiderivative of this, then I'm going to be left with f minus 4, or f to the fourth minus f to the first. So you would use your calculator. You would use your calculator to solve this problem, and that would give you your decimal answer. You're going to plug in for f of 1 equals 0. So whatever this says in your calculator is going to be what your answer is right here. Now, necessarily, if this had been like a 1, then we would have to add 1 to it, right? We'd have to move it over. But in this particular case, we do that, and our answer is D. And again, you guys will use Math 9 on your calculator to solve the problem. Okay, so that's it. That's all we have for this lesson. I hope these were helpful videos for you guys, and I'll see you guys in the next lesson.